Well, welcome, faithful souls. 8 o'clock in the morning on a wet, wild day. Okay, so this is the lecture you've been waiting for, basically. This is the one about choosing your statistics. And so far, well, the so far is in here as well. So in order to choose what statistics you need to... Ooh, that's really loud. You need to know your question, because statistics is about questions. Okay, statistics is designed to answer questions, and your questions will be about concepts. They might be about a single concept, but most of the time they're about the relationship between concepts. Okay, and at this stage, when we've got our conceptual question, we can narrow down the statistics that we need usually based on the type of question we've asked. And it's not until we figure out that the concepts become variables that we can figure out exactly what kind of statistics we're going to do. But the beginning of us deciding what statistics to do is to think about the concepts and how we want them to be related, and then figure out how to measure the variables. And once we've got that, we can start thinking about this. And there are 4 different areas of statistics. Well, there are some others as well, but these are the main ones. And there are 4 main types of questions you could ask. And over the past few lectures I've talked about them. There are questions that say what's going on, which is what descriptive statistics is for. You don't have a very specific question, you're just trying to figure out what's happening in a general sort of way. You can draw some graphs, calculate some percentages, and then you're done. You could ask a yes or no question, which is the most specific kind of question. And to answer questions of the yes or no flavour, you do hypothesis tests which produce p-values. And you could estimate a number. You could have a question where you want to know the size of a number, like what percentage of people blah, blah, blah. And to do that, you would use confidence intervals. And most of the time, you actually ask both of those questions in any research, a yes or no and a what's the number question. And then finally, you might want to predict or explain something, which is in fact usually the ultimate goal of most research, especially medical research. And you want to know what's the formula. So from some things, how can I calculate and predict what some other thing is going to be, mainly so I can control it in the future. And statisticians use regression for that. And I've talked about them in the previous couple of lectures. But choosing which one of those is about what sort of question you're going to be asking. I did say that if you want to ask a yes or no question, sometimes the quickest way is to do the whole regression process because it will spit out p-values for you. Right, that's the first step. Oh, okay, yeah. Just a reminder. There's hypothesis tests, and they have p-values, and the p-value helps you make the decision of the yes or no. And there are confidence intervals, and the numbers inside the confidence interval are the ones that you think are consistent with your data. Right, that's enough of that. So I've simplified what I did the first time and gotten it down to these 4 boxes, which are the main things you need to know in order to choose what statistics you need to use. So once you've chosen what kind of question you've got, then you can narrow down more into the data. So first you have to know exactly what variables are being measured. So, and that's all of them. So I've got these diagrams here to say, you know, I've got a banana, I've written down the age of the banana, the weight of the banana, the variety of the banana, the amount of potassium in the banana. I've got people, I've written down the temperature with chili, the temperature without chili, and also calculated the difference in those temperatures, and I've got a petri dish with stuff. Whenever I'm helping people do their statistics, the first thing I do is draw all of the variables involved. So you need to know what variables are involved. And then you need to know which of those variables are involved in your question, your research question. The next stage is to know what kind of variables are they. Are they numerical, meaning they're numbers, or categorical, meaning they're categories? And sometimes that decision is difficult to make, but most of the time, the best way to tell is that if how far apart they are is always the same meaning for the same distance apart, then they're really a number. Okay. So once you've figured out whether they're numerical or categorical, the numerical variables, you want to ask yourself, what distribution do you think they come from? It probably doesn't matter if you have a lot of data, so I'm not really going to cover this today. But there are some specific situations where a specific distribution of the data will specify a certain hypothesis test or other procedure. So approximately normal things where most of the values are clumped, and that height there is how likely things are. It's most likely to be near the middle and not so likely to be near the edge. Most of your classic ordinary tests that have been around for about 50 to 100 years, they'll be fine, and they're called parametric tests. But if it's skewed or, worse, a non-parametric test, which have only been around for a shorter time, they'll be a bit more appropriate. And if it's a Likert scale, it is Likert. I looked it up and heard him pronounce his own name. It's Likert, not like it. So if it's a Likert scale, strongly agree to strongly disagree, your non-parametric test probably won't work. So if you've got a lot of data, you can probably pretend it's normal. And if you've got only a small amount of data, you want to split it into categories. So, all right. So that's not going to come up into it much today. And then finally, what do the categories tell you about how your data's set up? So this one was about the numerical variables that were involved. This one's about the categorical variables that are involved. I only actually care about the explanatory variables, the ones that are supposedly influencing the outcome. So it may be that my categorical variable will split my big group into independent groups. So in this situation, I have a whole group of people that all had yes for Chile, and they were a set of rows in my data, and another group of people that all had no for Chile, and they're a row in my data. So when I investigate all the people that have certain outcomes for that category, it will split the data into separate groups. That will specify a certain kind of statistical procedure. But on the other hand, I might have given everybody both a meal with Chile and both a meal without. So when I look at all of the values of yes for Chile, everybody's got one. And when I look at all the values of no for Chile, everybody's got one. And so what the Chile does is it's telling me to repeat my measurement of the outcome of interest. And so on the side there, I've got some pictures. At the top, I've got a single person to represent a whole group. And there's one measurement of the outcome I'm interested in. So it's not the Chile I'm interested in, but the temperature, because I want to know how the Chile affects the temperature. So one measurement of the outcome, whereas in the repeated measures situation, there's two measurements of the outcome, or possibly 3 or 4, depending on what situation we're in. So all of this information together is what tells us which statistics I need to do. And the best way to do that is with an example, which is why I've got my handout for you there. So I'm just going to switch to so that I can have two things on the screen at once. So I can leave this one up here and switch to the document camera. So those who are watching online, yes, you can see the document camera and you can't see the Prezi. But luckily for you, that by the time you're watching this online, it will be on a website where you can look at the Prezi in a different window. So that'll all be good. So this is my handout, and gosh, this document camera is way better than the one in the other lecture theatre. I'll just make it fuzzy just to match it up, right? Okay, so I'm going to do something here. I'm going to take the same research question, and I'm going to have 6 different ways of experimenting with that, of doing an experiment to answer that research question, and each of the different ways will correspond to a different... Each of the different ways will correspond to a different hypothesis test. And these 6 hypothesis tests are the most common that you will see in any research. And so that's why I'm covering these ones. And for the med students, those online might not be med students, but for you guys who are here, when I write my exam questions, they will cover these 6. Because they're the most common ones. Of course, in your actual research proposal or your critical appraisal, they might have anything, right? You might need to do multivariate logistic regression or something, which is not one of these. But for the purpose of the exam, these 6. But for the purposes of doing your actual other assessment tasks this semester, you'll have to focus a little more on the wider field. Anyway, so I'm going to do my standard Research question, does the amount of chili in a meal affect your body temperature? And there's my concept picture. Chili is an idea, and I want to know how it affects temperature, which is another idea. And my situation, I've got 6 situations. Situation A says one group has chili in their meal, one group does not, and we measure temperature after the meal. So what I'm going to do is I'm going to draw a diagram that includes the information I need from this Know Your Data circle. Okay, so my chili and my temperature have become variables now. So chili, what kind of a variable is that in this situation? Yeah, because they either have chili or they don't. It's yes or no. And temperature, well, I'm going to assume it's numerical. Thanks, Rob. I'm going to assume it's numerical. Because they haven't said otherwise, and usually if you can measure it numerically, you ought to. So I'm going to do that as a number. Okay, chili as a categorical variable is influencing changes in, or related to changes at least in temperature, which is a numerical variable. Okay, so here's my question. When I look at my individual people, what have I written down about each person? Well, I've written down what group they're in. And I've written down their temperature. Okay. Wrong screen. I've written down their temperature. And what I've done is I've measured the temperature once. So this outcome variable here has only been measured once per person. And each person is only in one of these chili groups. And so this is an independent group situation. Okay, so now I'm going to assume that I've got enough data that I don't have to worry about the distribution of that numerical variable. So this situation is what the independent samples t-test is for. Or some people call it the unpaired t-test, which is what I call it. So now you know. If you have 2 categorical variables being related to changes in a numerical variable, and it's an independent group situation, it's called the unpaired t-test. Sometimes called the independent samples t-test, sometimes called the two-sample t-test. There you go. There's no good naming system. It's something you're just going to have to remember. Let's look at situation B. In situation B, each person has both a meal with chili and a meal without chili at different times. We measure the temperature after both meals. So when we look at our individual people, this time we've got when chili's yes, a temperature, and when chili's no, a temperature. I'm still interested in how chili, which is still categorical, is related to temperature, which is still numerical. But the difference is my data is structured differently. In the first situation, everybody was in one chili category and had one measurement of temperature. In the second one, everybody's in both chili categories and has 2 measurements of temperature. This is a repeated measures situation. I've repeated this outcome measurement twice. So this outcome, it's important that we're thinking about the outcome here, that outcome measurement has been done twice, so it's a repeated measure situation. And the name of the test that goes with this, it's still a t-test. T-tests are designed for numerical outcomes comparing across 2 groups or single groups, so it's still a t-test, but this t-test is called the paired t-test. And the pairs that it's referring to are these pairs of measurements that belong to the same person. So paired t-test. All right. Okay, so these two are, yep.
Sorry, just, so for the second one, what would you call you won't call them independent groups, you just call them
Repeated measures. So they're the two different situations, independent groups and repeated measures. Technically, any categorical variable can do either of them. So if you're in multiple situations, sometimes one category tells you to repeat the measures and the other one tells you to do independent groups, so it's a mixed situation. But I'm not going to talk about that generally here, but you can have what they call mixed methods. That's not mixed methods, mixed effects. Mixed methods is qualitative and quantitative. Sorry, mixed effects, they call them. All right. Well, here we go. We're going to change our situation one more time. Well, you know, still got 4 to go. So in that one, the thing that distinguished between these, there's still the same relationship with the same variables. It's still two categories relating to a numerical, but it was independent groups versus repeated measures. This one, let's see what happens here. One group has chili flakes, one group has chili sauce, and one group has no chili. Measure the temperature after the meal. Okay. So this time, what I've written down about each person is 3 different possibilities for chili. And each person's in only one of those chili categories. And then I've also written down the temperature. So in that sense, it's very similar to the the unpaired t-test. And my diagram is, well, my chili's 3 categories. And my temperature is a numerical variable. Great. So, this is an independent group situation. It's just that there's 3 groups. Each person is in one chili category, and that means that what we end up is 3 chili groups. Okay. So, with the t-test only applies when there's 2 categories. I could conceivably go, well, let's compare these 2 chili categories and these 2 chili categories and these 2 chili categories and do 3 t-tests. You could do that. But there is one testing procedure which covers all of it at once, and it's called analysis of variance. And it's normally shortened to ANOVA. So, ANOVA is designed, well, for multiple different things, but this ordinary plain ANOVA is designed to deal with the same situation that the unpaired t-test does, but with multiple categories. It'll work with 4 categories, 5 categories, 100 well, 100's a bit excessive, but it'll work with more than 2 categories. Technically, if you had 2 categories, you could still do ANOVA and it would work. It's just that people would feel uncomfortable because the t-test has been around longer, and so they feel better about it. So, yeah. And the t-test, because the t-test has been around longer, people feel more comfortable. So it's better if you've got 2 things to do a t-test, even though the ANOVA gives you the same results. So, what the ANOVA is not so good at is providing confidence intervals, whereas the t-test is good at that. So, what will actually happen when you do ANOVA is you'll do an ANOVA, and the ANOVA will not tell you which group is different to which. It will just tell you that they're not all the same. So it'll give you a p-value, and the null hypothesis is that they're all the same. And so if your p-value comes out low, you go, well, they're not all the same, but it doesn't tell you which one's different to which. So you will actually have to follow it up with 3 t-tests to compare groups to groups. But you're supposed to do the analysis of variance first, because then if you get a high p-value, you can just stop. You say, they're all the same, stop. And there's a whole lot of other things about inflation of type 1 error. And also, it's okay to just say ANOVA, because people will assume that that means following it up with t-tests anyway. So if you're in, say, Prism, and in the computer program Prism, and you ask it to do an ANOVA, there's a box to tick in that procedure that says, yes, please do the t-tests. And it will just spit it all out at once, just like a regression. All right. Next one. This time, my groups are given 0 grams, 0.5 grams, 1 gram, and 1.5 grams of chili powder. I really need to change this because I'm probably going to kill the last group. But anyway, so need to get it maybe in milligrams. So these groups are all given different numbers, and I measure their temperature after the meal. Okay, so this time I've got my people, and about each person I can write down what level of chili they had, and they also have one temperature. And the temperature, I'm assuming, is a number. And chili, well, I could do it as 4 categories, and then it would be ANOVA again. But since it really is a number, you know, everybody's got a number for chili. I could think of chili as a number. Everybody's got a number for chili and a number for temperature. Okay, since there's no categorical variables, I don't have to worry about figuring out what the categorical variables tell me. I don't need to worry about being an independent groups or repeated measures because that's only for when there's categorical variables involved. I don't have to, normally you'd have to worry about a normal distribution somewhere. You actually only need the outcome variable to be normally distributed. The input one, the explanatory variable, can be whatever you want. Okay, so that's fine. The situation I would use to do this would be regression. Some sort of regression, probably linear, but I'm just going to say the word regression to cover all of it. Now what the regression will do is it will create a formula that I can put the value of chili in and it will spit out the average value of temperature for that amount of chili. Oh dear. For that amount of chili. But it will also, in that process, spit out a p-value to tell me if the relationship is really there or not. So that's why I say regression, because regression will not just give you the formula, it will also give you a p-value to say whether the relationship exists. You'll note that I'm only talking about hypothesis tests here, because that's generally what you mention when you talk about the statistics section in a research paper or a research proposal. Situation E. One group has chili in their meal and one doesn't. Each person is asked if they feel hot or not. So chili's now back to 2 categories. It's not a number anymore, it's a category. It's yes or no. And each person I've written down what level of chili I gave them, none or some. And the temperature is now category 2 because it's just hot or not. So it seems redundant to draw the second diagram with the relationship, but I just feel better about it. And then it looks like I've done more. So this time, temperature is just a yes or no. It's a category now. I can't use a t-test because the t-test is specifically designed for numerical outcomes. My outcome is a category. Now, there is a categorical variable over here doing some explaining of the changes in temperature, so I'm going to need to decide whether it's independent groups or repeated measures. So let's see. Everybody's in one chili situation, okay, and that means the chili situations are defining separate groups, and they've only got one measurement of the outcome, where by measurement I mean writing it down. So everybody's got one measurement of the outcome, they're only in one chili category, so those chili categories define independent groups. So, independent groups, categorical, related to categorical. The most common test that people use to talk about that is the chi-squared test. Some people most of the time if you just say the chi-squared test, people will know what you mean, but technically it's for association. Because there's more than one kind of chi-squared test. So, and don't pronounce it chi, that will just annoy everybody. Chi. Okay, one final situation. Each person has a meal both with chili and a meal without chili at different times, right? They are asked if they feel hot or not after each meal. So let's think about these people. Their temperature is, just a second, or do I have an eraser? Yes, I do. Their temperature is hot or not, right? But we have their temperature in the chili yes situation and their temperature in the chili no situation. Right, so chili is still yes or no, and temperature is still hot or not. But now it's a repeated measure situation. Every person is in both chili categories, and every person has had their temperature measured twice. And so I've repeated the measurement of the outcome, so it's a repeated measures. Now it would be awesome if this was called the paired chi-squared test. It's because you've got like an unpaired t-test and a paired t-test for your independent groups and repeated measure situations, and it would be awesome if there was like an unpaired chi-squared and a paired chi-squared. Incidentally, you do actually use a chi-squared statistic when you do this hypothesis test. It's just named after the person who invented it rather than named after the chi-squared statistic. So this is McNemar's test. But if you like, in your head, you can think paired chi-squared test. Because you still use a chi-squared, you just calculate it differently based on the pairing. And the difference between the ordinary chi-squared test and McNemar's test is independent groups versus repeated measures. So these are the 6 most common. You won't see McNemar's test that often because some people will often do something else entirely. They'll usually figure out whether the temperature matched in both situations and then write down whether it, matching, yes or no, and then it pulls it back into a different type of test. But that's always possible, and I will talk about that next week, some of the details of these things and how they work specifically. But today, those are my 6 situations. Okay. What I'm going to get you to do is talk amongst yourselves about the ones that I have given you here. I've got heaps of them to try, and the nice thing is that you'll see my answers online, probably not till Monday, but you'll see my answers online if you get there, and we will go through some of them together. But for now, what I'd like you to do is chat about them for 10 minutes or so, and then we'll have a chat about a couple as a whole class after that. So what I've done is I've done a description of a research situation, and you need to decide what stats analysis to do. If you feel comfortable not drawing the diagram, go for it. I can't do it without drawing the diagram. If the stick figures, however, help you out, that's what they're for. So feel free to go for it and decide what statistics goes with each situation. Incidentally, this is the sort of exam question I'm writing. It'll be in the multiple choice section, but it will say, research situation, which of these 5 hypothesis tests are you going to pick? And they'll all be like that, because that is the skill I want you to have. And so that's what I'm going to examine you on. How many the MLT chooses to put into the exam is a whole different question. Last year I wrote 8 and they only put 4 of them in. So, yeah, anyway.
Oh, yeah, so this is supposed to be no, it's supposed to be
Alright, unfortunately, I would really like to, well, I have to go and have my yearly, performance meeting with my boss at 9. As much as I don't want to go, because it's so boring, I will try and finish on time today. So, having looked at everybody's, doing a great job. One of the nice things about this is that if you do think about it in this way, the categorical versus what kind of variable, repeated measures or independent groups, it's a lot easier than trying to just guess randomly. So I'm going to pick a couple and do them. But just so that you know to check yourself, number 1 was a chi-squared test. Number 2 would be an unpaired t-test. Number 3 would be a paired t-test. And number 4 would be ANOVA. All right. Okay. I'm just going to find a good one. Sorry? Yes, we can. Okay, let's have a look at this one. This number 8 isn't on my original list of examples. Okay, because it's not about a relationship between two variables, and all of those 6 that I did originally about relationships. I'm going to do this and I'll tell you what it is. Okay, so we have are the majority of people in favour of an unhealthy food tax? Okay, so I've got this concept of favouring tax, and I just want to know more about it. I'm not currently interested in what influences that decision, but usually if you were going to do this research, you would collect demographic data and try and figure out what influences that decision. However, today we're just interested in the raw number. So a large survey asked people whether they're in favour of an unhealthy food tax, whether they are in favour or not is recorded. So for each person, all I write down is in favour, yes or no. Sweet. That's all I've done. So all I have is a single variable, which is categorical. And I just want to know more about it. Alright. I haven't measured people of that one variable multiple times. I've just measured once. And it's not like it's really independent groups, because that's really about figuring out what happens afterwards in response, when there's something responding to this. So it's just a single variable. And I'm interested in how many are in favour. There's a name for this test. Most people would do the Z test for one proportion. That's what it's called. So I'm interested in a percentage, and the mathematical name for percentage is a proportion. I think that's the percentage as a decimal. And so it's a test for a proportion. And it's normally done with a Z test, just because that's the appropriate thing. Some people might do what they call a binomial test. Some people might do a chi-squared goodness of fit test. They all produce the same results. Though the binomial test will give slightly different results because it's done more accurately. But that's what it's called. What I have online is... And I really... Oh, damn. Anyway. I think the bench still has a mic. What I have online is a document which has a big list of most situations you could think of combinations of variables and stuff, and it says what you would normally do. And it doesn't just say what you would do in the yes or no question situation, it also says what you would do in the regression situation, like in the modelling situation, or in the confidence interval situation. It'll give you what the most common thing people do in those situations are. But I didn't print it today because it was very early in the morning. And it's just easier to look it up online because then it's in glorious colour and stuff, like blue and yellow. So, cool. I do want to do one of the ones that you've already done, but only for a specific reason, which is not necessarily the best reason, but you'll see what the reason is shortly. Does eating strawberries make ulcers grow more slowly? Two groups of... No, I undo the rabbits. Rabbits are randomised into three groups. One has all their food delivered by a machine, one has all their food delivered by a person, and the third is given cuddles. When the food is delivered after a month, the volume of plaque build-up is measured. Okay, so each rabbit has care, which is measured in three ways, and plaque, which is a number because it's a volume. And I'm interested in how care is related to plaque. And let's see, every rabbit's only in one situation, one care situation, and they've had their plaque measured once, and so this is an independent groups, which is ANOVA. And the only reason I want to do this is to show that you don't have to draw a person. Could also be a rabbit. Oh, sorry. They're not breasts. You can be as accurate as you like. So, you know that you don't have to, because so far I've drawn bananas and guinea pigs and geysers and cars, but, this makes my statistics experience better. So there you go. That's all I sort of had to say today. Thank you for being here so early in the morning. I'll see you again next week, and I'll talk specifically about some more of these tests. And then later on I'll actually take requests about basically anything statistical, and I'll actually, I get to see what all your papers are for when you do your critical appraisal. You have to write what stats you see there. I actually take that list and try and cover the most common things. So anyway, later on I'll take requests, but for now that's enough for today. Thank you very much, guys.